Hello, welcome to Bay College's Intermediate Algebra online lectures. Today we're covering section 8.8, which deals with applications of exponential and logarithmic equations. I know how we feel about application problems. It is story problems. So let's just jump right into it here. If you're following along in the notes, here's the very first example of an application problem where we have an exponential equation and we have to solve for something. And the question asks, how long does it take to double your money in an account that is compounded semi-annually at 6%? This is the equation we know. This is the compound interest equation. And we know A is the amount after some time t of an initial investment, P our principal, at a specific rate and a number of compounding. So let's define what our variables are according to the story problem. Well, it says, how long does it take to double your money? Well, to double my money, that means twice what I put in. So this is twice the principal. It hasn't actually defined what that is. The principal, well, it doesn't really matter how much it is according to this. We just want to know how long it takes to double it. So let's just keep that as P. How long does it take to double an amount of money? Our rate, well, it says 6%, and we know that's a decimal of 0.06. N is our semi-annually, which means twice in a year, so our N is 2. And the fact that it said how long does it take, well, that's our variable, T, the time. We do not know, so I put a question mark there. So let's take this information and plug it into this equation and see where our missing piece is and how we go about solving it. So I have my amount, well, that's 2P, and my principal is just P times 1 plus my interest rate of 0.06 divided by the number of compoundings, 2, raised to the number of compoundings times the time, which we don't know. So if we look at this, well, this is an arbitrary amount at this point, but our variable is in the exponent position. So this is an exponential equation that we have to solve. So I'm going to do a little bit of simplifying here. 0.06 divided by 2 is 0.03, half of 0.06. And I'm going to add 1 to it. So let's just 1.03 to the 2t equals 2p. Now my goal is to get this base isolated because that's where my variable is. It's to the power of this base. So I can divide both sides by p, and this is why it's an arbitrary amount. If I divide this side by p and this side by p, we can see that the p's actually reduce away. So we don't really have to worry about that as a variable. So we have 2 equals 1.03 to the 2t. Now it doesn't look too complex at this point, but our variable is still in the power. So we can use a logarithm to undo this exponential equation. So I'm going to jump right straight to a change of base and use the properties of equalities. I'm going to take the natural log of both sides. If I take the ln of this side and I take the ln of this side, now this, the ln of this whole side, this is my power, 2t. And I could write it here, but knowing my rules of logarithms, this power I can bring up front using the power rule 2t. So now we notice that we got our variable out of the exponent. Now I just have to isolate it. And I'm going to do that right here. I'm going to take the ln of 2 and I'm going to divide it by 2 and ln of 1.03. So ln of 2 divided by 2 and ln of 1.03 equals t. This is the exact answer. T is this value, but we're asked to find the time, right? Maybe in years. That is the case when it comes to interest because it's compounded annually or semi-annually. So we have to plug this into our calculator. Being that I already did the change of base when I took the ln of both sides, this is something I can put in my calculator. Make sure you use those parentheses. And when we plug this into our calculator, it's an irrational number that we have to essentially round at some point. So I get t equals 11.725 and our units of years. All right, and again, this is just an approximation because this is the calculator answer that we have to round at some time. So now we've answered the question. And does it make sense? If I'm investing some money at 6%, in a little under 12 years, I will double whatever it is I put in there. So we did solve the question. And you notice we used all these rules of exponential and logarithms to solve this equation. So if you're following along in the notes, take a look at the next example and try to work that on your own. If you want to pause the video and try it, it's basically a plug and chug type of question. We're going to actually skip the next question after that one and take a look at half-life. Now half-life is defined as the amount of time that it takes a substance to decay or break down to half of its original quantity. So this A naught is the original amount we start with. After some time t, and this is our coefficient of decay, how long is it going to take so that we have half of it left? Well, it's very similar to that previous example that we just did. We're talking about some value decaying to half. Instead of some value doubling, like we had in the last example, we're looking at some value decaying to 1/2. So this will be 1/2 the original amount. So just to kind of save time, we want to determine the half-life. So if I pick some arbitrary amount, if this is one amount, this will be half of that amount. So we can just write it as, let's say 0.5, 1/2 equals e to the negative 0.045 t. Now, why don't I have my a and a naught? Well, if I think if a naught is 1, this is going to be half of that value. That's the definition of half-life. So a single half-life, we're going to find t, determine the half-life, just a single half-life. So now how do I get rid of this e? Because my variable is still up there. Well, I can take the log of both sides. And because this is e, I'm going to use the natural log, because that is of base e. So if I take the ln of this side, 0.5, and I take the ln of this side, well, let's just write it right here for a moment. ln of e, the bases are the same. I can pull that power out front using my power rule, and this simplifies to 1. Or, I can just think of it as ln of e simplifies to 1. This is all that's left, negative 0.045 t. Now, to get t by itself, I just have to divide by this value. So I get ln 0.5 divided by that value, negative 0.045 equals t. This is the exact value. So now that's something I can plug into my calculator. I can hit ln of 0.5, hit enter. Divide that answer by negative 0.045, hit enter, and I will know what t is. And if I do that, I'm going to have to approximate, because that's what calculators do. I'm going to get 15.403. And just to be sure we know what's going on, t was in hours for this example. So my answer is approximately 15.4 hours, or 403. At this point, try to do example number 3 in the notes, and see how that works out for you. So this is just 2 examples, and if you have any questions, feel free to contact me. This has been section 8.8. Thank you for watching.